Today we're going to talk about sinusoidal functions and their transformations. So to review just a little bit, let's talk about just regular translations that we've talked about before. First of all, when we're talking about translations right here, we're talking about shifts up, down, left, or right. So these are just slides in the graph. If I have an equation like f of x equals x squared plus 3, this 3 is added out to the end of the function. I would know that this is a quadratic, so it's the quadratic function because I see the x squared is shifted up by 3 because when we have a number added to the end, that is going to shift our graph up or down. If I have a number added or subtracted on the inside of the parentheses, then I know that I'm shifting left or right. So for example 2, this is a cubic function. I know that because of this cube that I see here. And it is shifted to the right by 5 units in this case. Remember that we go in the opposite direction of the sign when we're on the inside of the parentheses. So vertical shifts, when we're talking about sine functions, affect the midline of the sinusoidal function. The midline of just regular sine of x, or we could say cosine x as well, would be just the x-axis, or the equation for the x-axis is y equals 0. So if we see a question like example 3 where we're asked for the midline of f of x equals sine of x plus 1, this is just a graph of sine of x shifted up 1, which is going to also shift the midline up 1, and our midline here is just going to be 1. So there are lots of transformations that can happen to a sine or a cosine graph, and what you see right here, f of theta equals a sine times b theta plus c plus d, is going to be a very standard form of a sine graph that we're going to see. If we see this and we're asked for the midline is really only affected by shifts up or down. And this plus d right here is our shift up or down in that graph. So whatever we have for the midline, or whatever we have for that d right there is going to be our midline. So our midline for this would be y equals whatever that d value is. Okay. Horizontal shifts affect the position of the function, but they do not change the amplitude, period, or midline. For sine functions, horizontal shifts are also called phase shifts. So, for example, with number 5, I've got f of x equals sine of x plus 5. We see that we've got this plus 5 added on the inside of the parentheses, and that's going to be a horizontal shift, and it goes the opposite direction of the sign. So this would be a phase shift to the left 5 units. Okay, so whenever we have a phase shift, we will be looking, so on this last question here, on this slide, what is the phase shift for f of theta equals a sine b theta plus c plus d? We can see the plus c is what does the phase shift here. I'd originally had written down left c, but we don't really know whether c is positive or negative, so probably the best thing to write here would be that this is a horizontal shift negative c units. So that negative would mean we're going in the opposite direction of whatever sign we have for our c. Okay, dilations are going to either compress or stretch out or expand our function vertically or horizontally. So whenever we multiply out front, by a number that is greater than 1. We are going to see that the fact that it is outside of our, in this case, absolute value bars, but it could be, like we're going to see in 9 and 10, square roots. It can be parentheses, whatever we have here. Then that's going to be vertical. So this is going to be the absolute value is the type of function that we're dealing with. That function is going to be expanded vertically by a factor of 3. The word expanded specifically tells us that we're stretching that out vertically, but it is okay right here to just say dilated. And dilated is a less specific term that just means that it's either stretched out or squished down there. So you could use that in place of expanded if you would like. For 8, we see that we have the number 0.25. And so this is still an absolute value function. But this time, because that number is lower than 1, in between 0 and 1, we are going to say that this is compressed vertically by a factor of 0.25. Now our next two are square root functions. So this is the square root function, and this time we see that number that we're multiplying by is on the inside of the square root, which sort of acts as our parentheses. There are not any parentheses written here, but we could put them there to sort of help us out. And so this time I have a number between 0 and 1, like a small number, but everything on the inside of the parentheses is backwards. So this is actually going to be an expansion. So it is expanded horizontally by a factor of, and this factor we have to use the reciprocal. We have to flip that fraction, and we'll just get 2 over 1, which is, of course, just 2. And then finally, we have another square root function. And this square root function is going to be compressed horizontally by a factor of 1/4. So again, we have to use the reciprocal of that number for this. And all of these words, expanded, compressed, those can be replaced with dilated instead of expansions or compressions if we choose. It's just a less specific word to use there. When we're talking about vertical dilations of sinusoidal function, this is going to affect the amplitude of the function. These are going to be very simple to do, actually. They're kind of harder to think about what they look like, but they're very simple to find the amplitude for. So if I go over here and open up Desmos, and I graph f of x equals sine x, and then I can go over here and do f of, or I'll call it g of x, equals a sine x. I can put a slider right here. You can see as I make that number a bigger, you can see the graph grow higher there. And this is going to be pretty straightforward. That amplitude is just going to be the value of that number that's being multiplied here. So my amplitude for this one would be 5 for that. Okay. Now it is important to note amplitude is always positive. So like if I have a negative value here, it is going to flip the graph upside down, but the amplitude, which is just our distance from our midline to our highest point, is always a positive number. So whenever we talk about the amplitude of this very generally, we are going to get our amplitude from this A right here, but we want to say that the amplitude equals the absolute value of A. And that is just because the amplitude of a function is always positive. If you already have a positive number like we had on example 11, you just use that number for that. All right, on to our next slide. Horizontal dilations of a function are going to affect the period and the frequency of the function. So let's go back over here to Desmos to examine sine of 3x. So if I, again, just have sine of x, and I graph g of x equals sine of 3x, you can see how that graph is kind of squished in. In fact, if we'd rather do it with a slider here, I can add a slider, and you can see as that number gets larger, it squishes my graph in, almost like an accordion. And then if my value gets smaller, it actually stretches that graph out further, horizontally speaking. So the period is a little bit more difficult to find. Normally, the period of sine is 2 pi, right? So so period of sine x is 2 pi. And that should make sense because that's the time that it takes to get all the way around the unit circle. So this is going to be a horizontal compression by a factor of 1/3. So this is just going to make the period of the function 1/3 of what we would have for just sine x. So the period of f of x is going to equal 2 pi times 1/3, and that will just be 2 pi over 3. That'll be our answer here. And so if we want to find the period, we also have to give frequency. And we learned yesterday that period and frequency are reciprocals of each other. So if I already have the period, all I have to do to find the frequency of f of x is just use the reciprocal, flip this fraction here, 3 over 2 pi. So if we were looking at this in general, we're going to be looking at this b value right here, but it's important to note that the period does not equal that b value. The period of a function is going to equal 2 pi divided by that b value, because we're going to be using the reciprocal, so that's going to go in the denominator. If I want to know the frequency, then I would use the reciprocal of period, so that would be b divided by 2 pi for this. So on this next slide, we just sort of have a summary of all of this stuff put together, because we're going to see this form of an equation really often. And you will note that it says sine right here, but it really doesn't matter if it is cosine instead. Sine and cosine functions have all of the same properties that we're looking at here. This would be the same if this were cosine. The amplitude is going to be the absolute value of the A. Period is going to be 2 pi divided by B. Our phase shift is going to be the opposite of C, so negative C, meaning that if I have a positive C, then I would actually go in the negative direction C, or left C. My midline is always y equals whatever the D value is there. And then frequency is just the reciprocal of the period, so that's going to be B over 2 pi. And so this is important for us to have memorized. It's really going to help us answer a lot of questions about sine and cosine functions. Okay, let's put this together and answer some questions about these problems. So if I look at this first equation, this is not quite in the form that I just saw. I may want to put some parentheses around that x. This 4 is not inside of the parentheses. If it were, they would have parentheses there like we see on number 16. So my amplitude is just the absolute value of this number here. So that would still just be positive 3. I think midline is the second easiest to find. So that midline comes from this number right here, which is that 4. This midline will be y equals 4. Okay. You should get an answer for everything except for phase shift on this one. Phase shift is the only one that we can say none to. You always have an amplitude, you always have a period, you always have midline, and you always have frequency. But phase shift, sometimes there's just not one there. And this graph is not shifted to the left or the right, so this will be none for the phase shift. And there is no number in front of my x right here, which means the period does not change. It just stays the same. Or if you want to think of it this way, there's a 1 there. So to find the period, you would do 2 pi divided by the b value, which is 1 right here. And you're just going to get 2 pi. Frequency is the reciprocal of period, so that's going to be 1 over 2 pi. If we look at 16, my amplitude here comes from this number out front. So the amplitude of this problem right here is going to be 1/2. The period, we don't have a number in front of this x right here. If we did, it would just be a 1. So the period is going to be 2 pi. That means frequency is 1 over 2 pi again here. This time we do have a phase shift. We've got this -3 that shifts this graph to the left or to the right. You're going to go opposite direction, so that'll be right 3. And our midline, we don't have a number out here on the end, but you always have to have a midline. Phase shift, remember, is the only thing we can say none to. So we have to think about what number we could add to the end that wouldn't change anything, and that's going to be 0. If you add 0, it doesn't change the value of this function. So the midline for this function is just y equals 0. Moving on, let's look at these problems. For 17, we've got a little bit of an issue. So that formula that you guys saw on that a couple slides back looked like this. You had f of theta equals a sine, and then you had parentheses b, another set of parentheses, theta plus c, closing 2 sets of parentheses, plus d. So if you have a value for b and c, b must be factored out. So we've got to do a little bit of work right here to get the answer right for number 17. So the 2 out front just stays where it is at. I have a 2x plus 4, so I could factor a 2 out of that and write it this way. 2 times parentheses x plus 2. And this is the form we want this in to answer this question. So I have a lot of 2's in this problem, so I'm going to point out where each thing comes from. The 2 out front is where my amplitude comes from. So I get an amplitude of 2 because of this front 2 here. For the period of this function, I want to look at this 2, the b value right here. So I will do 2 pi divided by that b value, which is 2. 2 pi divided by 2 is going to reduce, and I will just get pi for my period. Now that I have this factored out, I can see that my phase shift is going to be left 2. If you fail to factor that out, you're going to get the phase shift wrong, because if you just look at the original, it kind of looks like the phase shift is -4, but that's really not the case here. For this function, much like the last, I do not have a number added on here to the end, So I could just put a plus 0. My midline is going to be y equals 0. And frequency is just the reciprocal of the period, so that is 1 over pi. For 18, we're going to need to do the same thing that we did for number 17. I have both a b value and an extra value over here, and I want to be in this form where I've got the b factored out. So this function will look like this: cosine of 3 parentheses x minus 2 plus 4. So I'm just factoring a 3 out of both of these here. If I multiply this back, 3 times x is 3x. 3 times negative 2 is negative 6. So this is still equivalent. Now this one looks like it does not have an amplitude. You must have an amplitude every time. You cannot say none. So we got to think about what number would be out front right here in front of cosine, and that number is going to be a 1. So the amplitude there would be 1 for this problem. My period is going to be 2 pi divided by my b value. That b value is right here. That is a 3. My phase shift is going to be the opposite of this number, so that's going to be right 2. My midline comes from this last number here that's a vertical shift, so that's going to be y equals 4. And then frequency is just the reciprocal of the period, so I need to flip this fraction right here. 3 over 2 pi would be my frequency. Okay. Sometimes we're also going to have to write functions for this. So we're keeping in mind here that we've got that formula, y equals a sine of b times theta plus c plus d. Right? So if I have an amplitude of 4, that means that my a value is going to be 4. I'm going to have sine. I am going to leave the b alone for a second. And then I'll have theta. Phase shift of negative 2 means that I'll have a positive 2 right here. And then a midline of 0. So that's the d value there on the end. Notice I kind of stopped here with the period. My period is 2 pi. What I see kids do incorrectly a lot is they put the 2 pi right here. But to find period, we do 2 pi divided by that b value. So if my period is 2 pi, then that just means my b value was 1 right there. If you want, you can create yourself like a little equation. It's not so necessary right here. The period is 2 pi, which is going to equal 2 pi divided by b. So if you're solving for that b, you would multiply by b. Then you'd have b times 2 pi equals 2 pi. And then you would divide by 2 pi, which would give you 1 for that. Now, some of these numbers are unnecessary to be in this equation, so the answer would probably end up looking like this. 4 sine of, we wouldn't write this 1, we would just have theta plus 2, and oops, we wouldn't even put the plus 0 on the end. It would just look like this. Okay, so we're going to do this again with a sine function for these characteristics. So amplitude is 0.5. That's going to go out front. I have sine right here. I'm going to hold off on the inside part for a second and go ahead and do midline because I think it's the easiest. And put my plus 7 over here on the end. This time for that b value, my period this time is pi. Period, which is pi, equals 2 pi divided by b. So in this case, that b value right there is going to be 2. Because if I plug in a 2 right here, 2 pi divided by 2 would give me pi. Or, if you would like, you just solve that equation by multiplying both sides by b. That gives you b times pi equals equals 2 pi, and you're trying to get the b, so you divide by pi, cancels on both sides, and b equals 2. And then we have a phase shift of 1, so we need an extra set of parentheses right here. And that phase shift, we could put theta minus 1. You're also okay if you want to use an x instead of a theta in this case. Here, theta is just a variable in this problem. And our last ones here, we've got a couple more equations to write. I realize now that I have said sine function for all of these, but it really doesn't matter if it's cosine. So I'm just going to switch this to cosine, just so we see that it doesn't matter. I like to do amplitude and midline first because they are easier to look at. I think I also do f of theta on this one. And amplitude is going to be 5. That'll be out front. I will have a cosine function. I'm going to hold off on the insides here for a second. They're a little tougher. And then my midline is -4, so I'll put a -4 over here on the end. Really, the phase shift is not that bad. I have a phase shift of pi over 6, or pi times 6. So I will just have theta minus 6 pi right here. On the inside, it's that number for the period that's a little bit tougher. The period is 3 pi over 5. And to find the period, we do 2 pi over b. So if I want to solve this so I can find the b, I would multiply both sides by b. So I've got 3 pi over 5 times b equals 2 pi. And then I need to get rid of 3 pi over 5. I'll have to divide that off. I here would multiply by 5 over 3 pi. And that is because dividing fractions is easy as pi. Flip the second and multiply. So when we divide by 3 pi over 5, it's really the same as multiplying by 5 over 3 pi. You can see everything cancels here. On this side, let's put this over 1 so that those are both fractions. The pi will cancel with this pi, and I will get 10 over 3. So 10 over 3 is the number that I'll get there on the inside for the b value. Let's look at this last one. Let's use an x on this one. This asks for a sine function with an amplitude, so let's call it f of x. And our amplitude is 60. Sine, let's hold off on the insides. And our midline is 150, so I'll put a 150 here on the end. Phase shift is not too bad to do. I have a phase shift of -10, which means I'll have x plus 10 here. I'm just using an x instead of a theta this time, just to show that it's okay to have whatever variable you would like. And then for the b value, I know to find the period, I would do 2 pi over b. So if I do 80 equals 2 pi over b, I can solve this by multiplying both sides by b. That gives me 80b equals 2 pi, and I would divide by 80. And so b is 2 pi over 80. That will reduce to pi over 40 if we divide the top and bottom of that fraction by 2. So pi over 40 is the b value. So most of these numbers just get plugged in. You can see the 60 goes here, the -10, we use the opposite sign and that goes here, and the midline goes here. It is mostly that b value you have to do a little extra work for whenever you're writing those sine functions. So you will have an assignment practicing this. Do your best on that. We will try something on every problem, but we will definitely spend whatever time we need looking at that tomorrow.